Alright, let's get started with 6.3, where we're going to introduce vectors into our coordinate plane. So, a vector, all it is it's a line segment, but it has direction now. So we have a starting point and a terminal point, an ending point. Okay? So it's a directed line segment. We can't go from one end to the other and back. We're going from one end to another end. Okay, the magnitude is just its length, and we're going to denote it with the double bars on the outside. Okay, and we can find the length using our old friend, the distance formula, which is the derivative of the Pythagorean theorem. Okay, all right. So if you have the same magnitude and the same direction, you are equivalent. So, for instance, these lines are all equivalent vectors because the angles and the distances are the same. If we put them all on the same starting point, they would all end at the same terminal point. Okay? Alright, so, one last thing that we use a lot. Lowercase letters are used to denote the vectors. Instead of saying from P to Q, we could just give this vector a name like vector V, and then write it as lowercase v in boldface. Okay, so that's how you'll know we're talking about a vector. Now a vector has a couple things going for it. It has a horizontal and a vertical component to it. Alright, so this one is over 3 and up 2. This one's over 4 and up 4 from this initial point of 1, 2. Alright, so in this one we need to show that they're equivalent, and that means that we need to show that their distances are the same, first and foremost. So the square root here, I'm going to do PQ. The magnitude of that with the double bars there is going to be, we're going to first do 3 minus 0 squared plus 2 minus 0 squared, which is 3 squared is 9, plus 2 minus 0 is 2, squared is 4, square root of 13. Okay? And then the other one here is going to be the magnitude of vector RS, and that's the square root of 4 minus 2 squared plus 4 minus 1 squared, which is 2 squared is 4, and 3 squared is 9, and we do get the same thing. Okay? Alright, so let it be the same and show that they are equivalent. Okay, the other thing we can do is on this one, if we move this down, we'd go down 2 and over 1 to start at the same spot. If this one went down 2, its y value would now be 2. And if it went to the left 1, its x value would now be 3. We're going to start and end from the same place. So those vectors are equivalent. All right. So go ahead and try problem 11. Alright, so the component form of a vector, all this is saying is that a vector is made up of horizontal parts and vertical parts. So let me skip this real quick and look at this one right here. Okay, the component form of a vector v that starts at 4, -7, 1, 2, 3, 4, -7, 4, 5, 6, 7. There's our starting point. Okay, and our ending point is -1, 1, 2, 3, 4, 5. Okay? There is a magnitude, that means go straight to it. And how long is that going to be? Right? So that's the magnitude of vector v. Okay? But the component form is the horizontal piece and the vertical piece. Alright, so the horizontal piece is we're going from 4 to -1. Okay? So that means we're going -5 in the horizontal direction. Negative because we're going that way. Okay, so this is the x value, the horizontal part. The y, the vertical component, we're starting down here at -7, then we're going up to +5. That's a vertical increase of 12. So to write this in component form, you're going to write -5, 12. To get from where we start to where we finish, we're going to go left 5 and up 12. The magnitude is just the distance between those two things. So that's the Pythagorean theorem. we can do this without doing the distance formula because a 5, 12, 13 triangle is a Pythagorean triple. So the magnitude of V is 13. And if you don't believe where that 13 came from, do the Pythagorean theorem with 5 and 12. The hypotenuse is going to be 13. All right? So that's what you have to do on problem 19. See if you can get the component and magnitude for vector V. Okay, so at this point, if we have all this in here, and the next few slides is a lot of saying if you have vectors, you can add them together and you can multiply them. Okay? So scalar multiplication means if you have some vector V and you multiply it, the angle stays the same, it's just the length changes. So half of V is V half as long. 2V is V, same angle, twice as long. Okay, vector addition means we're going to go tip to tail. We're going to say, okay, first we're going to do U and start from the initial and end at the terminal point of U. And then the terminal point of U becomes the initial point of V. And so if we put it together, we got here. And so there's something called the parallelogram law, which means that if we did V first and then U, we'd end up at the same place as doing U first and then V. Okay? But the easy thing with this is that if we just add the components together, add the x's and add the y's, we get U plus V. All right? So that's what this says here. If we're doing scalar addition, add the horizontal and add the vertical components. And if we're multiplying, you just multiply each piece by the multiplier. So quick example here. Let's do this. So 2V is we're going to just be 2 times whatever inside of V. So 2V equals negative 4 comma 10. All right, W minus V is going to be the W x component minus the V x component, comma, the W y component minus the V y component, 5 comma negative 1. And then V plus 2W, so V is negative 2 comma 5. And 2W would be 6 comma 8. And if we added those together, we can just go straight down here. We're going to get 4 comma 13. All right, so just basic addition and multiplication. Do the same thing on 31. All right, so a couple properties here. All this is saying is that whatever you can do to normal numbers, you can do to vectors. All right, the basic rules of algebra apply. Multiplying, dividing, all that good stuff. All right, so that takes us to the unit vector. Here's what the unit vector is. If I've got some vector, and let's call it, let's do the 5, 12 again, 13, okay? I want to know what the component form would be if my vector got shrunk to having a length of 1. Okay? And all you do with this is you take the vector 5 comma 12 and divide it by its magnitude. That's what this is saying here. Okay? The vector divided by its magnitude. 5 comma 12 divided by the magnitude is 13. So the unit vector would be 5/13 comma 12/13. Because if you did the Pythagorean theorem with 5/13 and 12/13, the hypotenuse length would be 1. All right, so if we do it with this one, negative 2 and 5, there's our vector, negative 2, 5, so 25 plus 4 is 29, so now our unit vector is negative 2 comma 5 over root 29. So our unit vector is negative 220 over root 29 comma 5 over root 29. And just like always, we need to rationalize our denominator. Negative 2 root 29 over 29 comma 5 root 29 over 29. And that would be your unit vector. Try problem 41. All right, so we can, instead of writing it in component form like this, 1, 0, we can say we're going to use I to be the vector 1, 0. So I is a horizontal unit vector, 1 unit in length. J is going to be a vertical 1 unit length long vector. So now if we have 2, -5 to 1, 3, we want to write it as a linear combination. Here's what we're saying. So from 2 to 5 and end at -1. So from 2 to -1 is 2 to -1 equals -3. From -5 to 3 is a distance of 8. So our unit vector in component form would be -3, 8. All right. As a linear combination, we're going to say -3i plus 8j. Okay. 3 negative I vectors and 8 positive j vectors. Gets us where we want to go. All right. So I is for horizontal, j is for vertical. All right, so give me that in problem 53. All right, vector operations, same thing here. We can just put them all together. 2u minus 3v. 2 of -3i plus 8j minus 3v. 2i minus 1j. And so that's going to be -6i plus 16j minus 6i minus, minus 3j. And so -6 minus 6 is going to be -12i. And 16 minus -3 is 19j. All right, so again, just your basic addition and subtraction. Try problem 59. All right, so now we want to be able to see if we can figure out the angle in here. If we have some vector going up like this, what's the angle in here? Well, the nice thing is we know the x and the y forms, right? So this angle in here, y over x, is tangent. So tangent of theta is b over a. And the one we really want to use, the one, if you're going to write notes from this slide right here, theta equals the inverse tan of your y over your x values. Okay? That's what you want to have for all of these vectors. All right, so find the direction angle of each vector. So on this one, for u, theta equals the inverse tangent of the y value, 3, over the x value, 3. For b, theta equals the inverse tan of -4 over 3. So let's go to the calculator and figure these out. First of all, 1 over 1 is 45 degrees. That's an easy one. Okay. 4 over 3 is not on the calculator, so let's grab the calculator. Come back, calculator. There you are. And I'm in degrees. Yes, I am. And so the inverse tangent of -4 over 3, -53 degrees. Okay, so we need to think about that for a second. -53 degrees. We want to be able to put this in the right coordinate, though. Find the direction angle of each vector. 3 and -4 is down here in quadrant 4. So it's -53 to go here. What is it to spin all the way around this way? It'd be 360 minus the 53. And so you get 307 degrees. So you want to be able to figure out which quadrant you're in. And you're going to start from the positive x value and spin around. All right, you're up on 63. All right, so a couple word problems to finish up here. And so I'm going to actually pause and go over the word problems in class together. So hold off on 8 9, and I believe there's a 10 as well. 8, 9, and 10 we will do together. So remind me that we're doing 8, 9, and 10 together. And other than that, any other questions, we'll go over them in class. All right, good luck.